All right, so in our last video, we did one example of finding the area between two curves. And what was different in that example compared to the one we're about to do is in the previous example, it told us exactly what interval we wanted to find the area over. It was the interval from -1 to 0. However, a lot of problems will not tell you what the interval is, giving you a little bit more to work out on your own. So let's read this one. It says that we're going to find the area of the region bounded by the curves y equals x squared minus 4x and y equals 2x. So what that means is that these two curves are going to enclose an area somehow. And from that, we're going to try and determine what the interval is that we're integrating over. You can't do any of that, well, it's difficult to do that without first graphing the functions. So pretty much every problem you do in this section, you're going to be starting with a graph. Let's take a look at the first function here, y equals x squared minus 4x. Notice I could write that as y equals x times x minus 4. And the reason I'm doing that is because when I look at this function here, I can see that it's a quadratic, so I'm going to be graphing a parabola. I can see that it's an upward opening parabola, and there's different ways of going about that. One way is to find the vertex of that parabola and then plot some points and reflect them across the axis of symmetry and all that kind of stuff you learn about in algebra. Another way, since we're not looking for perfect accuracy here, is to factor this. And then if I were to set this equal to 0 and solve, I would get the x-intercepts of my parabola. So I can see that 0 and 4 are going to be the x-intercepts I'm looking for. Let's put 4 right there. 0 is right here. And so I can see that my parabola is going to do something like this. Okay? Not perfect, but that's okay. It doesn't need to be. It's just enough to get the information that I need to solve this problem. Now the next function here is y equals 2x. I recognize that as a line with a slope of 2 passing through the origin. The y-intercept is 0 here. So I'm going to get a line, and because 2 is positive, it's going to be a positive slope. It's going to be going uphill as I go from left to right. Is that an inaccurate graph? No, it's not really, because for one thing, I can tell you that the slope of my line is probably too shallow. That looks more like it has a slope around 1, maybe even less than 1. Does that matter for what I'm trying to use this graph for? Not really, because if I label these, y equals 2x, y equals x squared minus 4x, I can pretty clearly see that the region I'm trying to find the area of is here. I can see that these two curves do enclose a region, and this is the only region that would logically make sense there. Within that region, I can see that 2x is the function on top, and x squared minus 4x is the function on the bottom. It's the curve on the bottom. So when I do high minus low, it's going to be 2x minus x squared minus 4. But I need a little bit more information. I need to know, when I set up my definite integral here, what my lower and upper limits of integration are going to be. And those limits of integration correspond to the x values, the values on my y-axis, or sorry, x-axis that this region lies over. So I can see that 0 is one. It's kind of like the left endpoint of that region. In fact, it's one of the points at which these two curves intersect. Over here, if I were to find this point of intersection and sort of drop this down here, there's some x value here that is representing the point of intersection of these two curves. I need to figure out what that x value is. So I can do that by setting these two functions equal to each other, because that's where you get points of intersection. I can set x squared minus 4x equal to 2x. That's not hard to solve. If I subtract the 2x over, I get x squared minus 6x equals 0, or x times x minus 6 equals 0, which means x is either equal to 0. Remember, that was one of the points that we found. That's my lower limit of integration, or 6. 6. That's where that point is. You can do a sanity check here. I mentioned sanity checks in the last example. 6 is larger than 4. And the way that I drew this, I can see that this value here definitely should be larger than 4, which is the x-intercept that I labeled there as well. You can also just plug it into both functions to make sure they come out the same. But now we have our limits of integration. Okay, now let's subtract the functions, and let's make sure we're doing that in the correct order. The high function is 2x. I want that to appear here, minus the low function, x squared minus 4x dx. Remember, parentheses around that second function is really, really important because that minus sign needs to distribute. Let's simplify. So if I were to distribute the negative in, I'm going to get negative x squared minus 4x. That's plus 4x. And then I have a 2x here, so plus 2x would make plus 6x dx. Integration here is straightforward. This becomes negative x cubed over 3. This becomes plus 3x squared, and we're going from 0 to 6. When I plug a 0 in, I'm going to get 0, so that's pretty easy to see, which means the only thing that's going to matter here is what happens with my upper limit of integration, the first thing I plug in. If I plug a 6 in there, I'm going to get negative 6 cubed over 3 plus 3 times 6 squared. That's all arithmetic. It's pretty straightforward. I'm going to leave that part to you, but this comes out to 36. Notice again, I got a positive answer. That's what I'm expecting to have happen with these problems. So my sanity check here passes. I'm not getting a negative answer. I don't have a reason to believe based on that I did anything wrong there. Let's keep going. Let's do something that's using functions that are not polynomials. Some trig here is going to be a nice change of pace. So it says find the area between the curves y equals cosine of x and y equals 1 minus cosine of x. And then they do give us an interval here from 0 to pi. X goes from 0 to pi. What's tricky about this example, as we're about to see, is that over that interval from 0 to pi, you're going to see a change in which function is on top and which function is on the bottom. So let's graph this to see what I'm talking about here. Go like this. So first of all, I'm going to graph the function y equals cosine of x. Now I know the function y equals cosine of x is going to look something like this, at least from 0 to pi. If I keep going and complete one full period of that function, y equals cosine of x, then I would come back up here and start where start back at 1 again. That's 1. Once I get to 2 pi. But because we're only integrating from 0 to pi, I don't need to sketch that much. Now, what about the function y equals 1 minus cosine of x? Can you sketch that by hand? I hope so. You should be able to. The way that we do that, I realize I need a little bit more space than I gave myself. Ignore the 1 for a second. Think of it as minus cosine of x. Y equals negative cosine of x. That negative there creates a reflection in this graph. So we're going to basically take this graph and flip it upside down so that we start down here and we go up here. But adding a 1 to that takes that whole thing and shifts it up 1 unit. So really, I'm going to be looking at a graph that does something like this. Okay? And it's going to go as high as 2 up here. Now, that's not really that important, the fact that it goes up to 2. What is important is that I'm looking for the area between these two curves over that interval, which includes this area as well as this area. Okay? And what makes that difficult is one of these functions is on the top, but then becomes the function on the bottom at some point. So if I label these, y equals 1 minus cosine of x, then I'm going to have to do 2 integrals. I'm going to have to do one for this first region here and one for this second region here. Let me call this one S1 and this S2. I want the area of S1, which is what I'm going to use that notation to represent. A of S1. That just means the area of S1. So in order to find that area, I am going to set up a definite integral. And I'm going to do the high function, which is cosine of x, minus the low function, which down here is 1 minus cosine of x. But what I'm missing is my limits of integration. I can see pretty easily that the left limit of integration, or the low limit of integration, is 0, because that's where everything starts here. That's where we're also told that we're starting here. But what about my upper limit of integration? It's not pi. Pi is way over here. And for this first little region, I have a point of intersection between these two curves, which will correspond to some x value right there. So how do I find that? I can find that value the same way I did it in the previous problem. I take the two functions, I set them equal to each other. Cosine of x equals 1 minus cosine of x. Then I solve this equation. If I add that cosine of x over, I'm going to get 2 cosine of x equals 1, or cosine of x equals 1/2. If you remember solving trigonometric equations in your trigonometry class, you should know that this equation has infinitely many solutions. But we don't really care about that because we know that the solution we're looking for lives right here, right? It's between 0 and pi. In fact, we can even do a little bit better and say that it's between 0 and pi over 2, because that's where this cosine graph would intersect the y-axis, and I can see that this should lie to the left of that. So that means I'm looking for a solution in the first quadrant of the unit circle to this equation right here. Where is cosine of x equal to 1/2 in the first quadrant? Well, that's exactly when x is equal to pi over 3, okay? So that is the x value that kind of divides these two regions. And that also would become my upper limit of integration here, pi over 3. All right, let's simplify the integrand before we do our integration. I have cosine minus 1 minus negative cosine. That's like a plus cosine. So cosine plus cosine is 2 cosine of x minus 1. Okay, this is an easy integral to do because the antiderivative for cosine is just sine. I have 2 sine of x. That becomes an x right there. And we're going from 0 to pi over 3. Now notice if I plug 0 in, my lower limit of integration, which would be the second thing that I do, sine of 0 is equal to 0. Minus 0 is still equal to 0. So I can ignore the 0 because it's not going to contribute anything. But when I plug a pi over 3 in, sine of pi over 3 is root 3 over 2. Then I multiply that by a 2, which cancels the 2 from the denominator, leaving me with just root 3. Minus pi over 3 would just look like that. Please, please, please do not go plug that into a calculator and give me a decimal. Because if you do that, you're giving me a rounded, inaccurate answer. This is the accurate answer. Write this. Okay, leave things in radicals and pies. It's much better to do that. Let's find the area of the second region now. A of S2. I'll do that over here. I'm looking at this region right here, and I know that pi over 3 is the left bound for that region, and pi, I can see, is the right bound. So we're looking at an integral that goes from pi over 3 as my lower limit of integration to pi as my upper limit of integration. And then I'm subtracting these two functions again, but I'm going to do it in the reverse order this time because now 1 minus cosine of x is the high function. So 1 minus cosine of x minus the low function, which is cosine of x. Now you might look at this and say, wait a minute, you didn't put parentheses around the second function, even though I did around the first function. And I know I made a big deal about putting parentheses around the second function before, but remember I said that's if this function has more than one term in it. There's only one term here, so I'm not going to have a mistake that I make where I forget to distribute a minus sign over multiple terms. It's okay to leave the parentheses off when there's just that one term there. Let's simplify things. 1 minus cosine of x minus another cosine of x is 1 minus 2 cosine of x dx. Integrating this is also very straightforward. I'm going to get x minus 2 sine of x from pi over 3 to pi. Okay? From here, it's arithmetic, right? It's just knowing your trig, what is sine of pi, what is sine of pi over 3, and making sure you set this up correctly. I'm going to challenge you to do that step on your own and see if you can come up with the correct answer from that. What this should come out to, if you do this correctly, is 2 pi over 3 minus root 3. Okay? Now, I have the area of two separate regions, but the answer is, the question, I should say, is asking me for the combined area. I need to add these two together. So the area of the entire thing is root 3 minus pi over 3 plus this guy, 2 pi over 3. Oh, I'm sorry, I wrote the wrong thing. That should be a plus right there. I was looking at my notes off to the right here. I was thinking something's not adding up correctly. Yeah, this was a plus. So I have a root 3 plus another root 3. Together, that's going to be 2 root 3, and then 2 pi over 3 minus pi over 3 would just be plus pi over 3. Okay? Positive. We need our answer to be positive, and that's clearly a positive number, so we're in good shape. All right, we have a little bit more to cover. We'll do that in the third video.